lesson just to see how we're feeling about um, drag and altitude and range. So I want you to use the PhET simulation one more time. So I've got the link right there. It'll take you to the usual same simulation we've been using before. And then the second link is to the do now itself. This is not graded, it's just a Google form. There are 4 questions and the instructions of what you need to do in the PhET simulation are in the questions. So it'll give us about, time is for 9 minutes maybe to do this. And then we'll come back together again. I'll be here listening if you got any questions, but otherwise you've got 9 minutes to work on the do now. We'll come back together to review it then. Go for it. All right, kiddos, 9 minutes has elapsed. Let's come back together. Looks like 11 of you have responded. So 3 more people still need to submit, but you can do that while we're looking it over. Answers were looking good, but just to make sure we're all on the same page, for the first question, when you fired the cannon from 60 degrees and 30 degrees, did they land in the same place? They shouldn't have. Anyone know why? Some of you got it. This
at a different degree, or like they're at a different angle.
They're firing at a different angle, but as we learned in the previous lesson, if you're firing at 2 different angles like that add up to 90, like 60 and 30, which were the 2 you used, they should land in the same place. And yet in the simulation, they don't. Some of you got it. Why though? Why are they not landing in the same place?
Because the cannon is higher, it's not on the ground.
Yeah, it's like 10 or 15 meters up, right? So if it was level, then they would. And so Cora, that's what we did yesterday. And that's something you can, if you want to, you can go back to the PhET simulation, lower the cannon down to 0 meters and fire from 60 and from 30, and it will land in the same spot. But so this was when I was first reading the chapter, I immediately opened the simulation to try it. And I was getting all frustrated. I was like, why aren't they landing in the same place? And it literally took me a minute to realize, like, oh, my cannon is 10 meters off the ground. I need to make it level. So part of that rule is that it has to be level. It has to be firing from horizontal with the ground. Very good. Most people got the angles to hit the statue of David that's down below. What angles did you use?
Like 75.
So 75 was one, but there's a second one you can use too. What else?
I think -40.
Yep, around -40, then you're just firing directly at him, right? So that's actually technically below horizontal. That's why it has a negative, right? -40. But yeah, there's always 2 angles. And again, those don't add up to 90 or anything like that because you're not firing from the horizontal level, the same level that the David's at. The cannon is above. So bonus question, as far as I could see in the answers, only one person got this. Why do you think they have the statue of David below? Some of you were thinking he invented the cannon, things like that. It was kind of funny. Has anyone seen the David? Anyone been to Florence?
Yeah, I've been.
Some people said it's for size, for like the scale. Does anyone know how big the David actually is? Is it life-sized?
No.
That's one of the incredible things about it, is that it's as tall as 3 different people. It's enormous. But one person knows the story. So David is a character from the Bible. Does anyone know what David's famous for? What did David do? There's one famous story about him.
Goliath.
David and Goliath, right? He took down this big, tough, sort of giant monster, right? Does anyone know what weapon he used to do that?
Like a discus?
Yeah, he used a sling with a stone in it, right? Which works just like a discus. It's something that he was throwing. And so it was a projectile. Get it? I think the programmers are just being a little nerdy, that it's a character who's well known for throwing a stone. One person got it. I'm not entirely sure who, but that's what that was getting at. And for the last question, when you apply in the drag simulation, once again, when you fire from 60 and from 30, when we did it in the previous, if you did the same thing in the intro, they land in the same place. Why don't they land in the same place in that simulation? What's influencing, what's changing things?
Is it air resistance?
Yep, it's the drag. And what I thought was interesting about this is that drag isn't equally affecting the 2 different launch angles, right? Because you would think if drag's present and it's always acting on a projectile, then they would still land in the same place. It would just be a little bit shorter than where it would be if there wasn't any drag, but that's actually not true. It's because drag is reducing both the altitude and the range in different ways that they're gonna land in separate places. So again, that 90% rule that, or 90-degree rule that if two angles add up to 90, the projectile land in the same place, makes two big assumptions. One, that you're firing from the same horizontal level, and two, that you have no air resistance. So it's not the most realistic thing, but good thing to keep in mind as we move forward. All right. Any other questions from the PhET simulation or from that do now? Okay, before we move on to the last part of chapter 5, I wanted to take a moment to review the homework you had from Hewitt. It was questions 21, 23, 24, and 25. Were there any of those that you were confused by, left blank, or wanted help on?
I was confused by 21. I didn't get the full parameter of it. Like let me look at it again. But
Well, let's look. Yeah, so 21, projectile is launched at an angle of 75 degrees above the horizontal and strikes the ground downrange. For what other angle of launch at the same speed would this projectile land at the same distance? So this is getting at that idea of if we're assuming there's no air resistance, there's no drag, and they're firing from horizontal. Remind me, what's the rule if you've got two angles that add up to what?
90.
Yeah, if they add up to 90. And so again, some people had a hard time with this. Some people were saying 25. Does anyone know what 90 minus 75 is? It's not 25.
15.
It's 15. Yep. So if you fired at a 15-degree angle, it would land in the same spot. Which again, it's kind of mind-boggling, but you can run it in the simulation and it'll work. Good question. Any other ones that you wanted to look over? All right. If you have not submitted your answers to those questions yet, please make sure to do so. I want to take a quick moment to go through some slides and review the last part of chapter 5. Feel free to take some notes, either in your digital notebook or on paper. And I'm going to try to use some poll everywhere questions just to sort of keep us engaged and make sure you're following along. Does anyone have any other teachers who've used poll everywhere before? Sort of a, you'll see how it works. Hopefully it should work just fine. It worked fine in my previous class. So, alrighty. So chapter 5.12 ends with talking about what are called elliptical orbits, and escape speed is what they call it, but I prefer using the term escape velocity. And so pictured here, right here, you can see an elliptical orbit. I'll talk a little bit about how that works and what's going on with the satellite at that in that type of orbit. And escape velocity, this is kind of silly, but if you were to, we always are familiar with that rule of what goes up must come down. If you are able to achieve escape velocity, then that doesn't apply. What goes up will just continue to go. So you should never try to toss a baby that high, period. But if you're able to get to escape velocity, then that baby's not coming down. That baby's heading into space. So, all right, our first poll everywhere question that I want to give to you, you should be able to see it right here. Is what are satellites? This is sort of a review of content from our previous lecture. So you can just open up a new tab on your computer and go to pollev.com/hatesci2, listed right there. Or if you want, just text the hate sci2 to 22333, and then you just text the letter of your answer. So we've got option A, B, C, and D in that order going down on the screen, and so should be running now. So go ahead and submit an answer to that. Again, we have 14 people in attendance. I'm going to give us about 30 seconds just to see, and then we'll look it over. All right, let's see how we're feeling here. Okay, most people went with C, but some people are feeling like they're the communication machines. The correct answer is indeed C. And the reason that when you hear the word satellite, the communication machine option comes to mind is because that's what we usually think of when you think of satellite, right? It's something we have launched into space, we use for cell phones, TVs. But in reality, you could call the moon a satellite. Earth is actually a satellite going around the sun. It's a sort of a general catch-all term in physics to describe anything that is rotating around. So keep that definition in mind as we continue forward. All right. So if we have any projectile moving fast enough to continuously fall around the planet, that is what we call a satellite. And the minimum speed required to achieve that sort of satellite status, as we talked about in our previous lesson, is 8 kilometers per second. And that's because that matches the curvature of the Earth, right? Earth curves downwards about 5 meters every 8 kilometers, and it takes about 1 second to fall 5 meters. And so that sort of matches that. If you can achieve that horizontal speed, you'll have a circular orbit. Chapter 5.12 is asking, okay, well, what happens then if we're going a little bit more than 8 kilometers per second? Then you are going to achieve what's called an elliptical orbit, and it's exactly what it sounds like. It just means that the satellite is now orbiting in an elliptical shape. An ellipse is sort of a wide circle that they say mathematically it has 2 foci, or 2 points that it is generated from. You can actually draw a pretty good ellipse on your own if you're able to get some tacks and string and a pencil. You could put 2 tacks down on a piece of paper and usually attach like a string or a piece of floss. And if you hold it taut using a pencil and then just go around in a circular motion, it will draw what is called an ellipse. It's just a slightly expanded circle. Now, this gets interesting in terms of orbit, in terms of how things behave, how the satellite behaves when it is in an elliptical orbit. And so I just want to see, use another poll everywhere question and see what you guys know. You can take your best guess on this next one. So same website and address. The question is, how does elliptical orbit affect the speed of the satellite as it travels? Option A, there's no effect. Speed of the satellite is consistent, does not change, even in an elliptical orbit, just like in a circular orbit. Or it goes faster as it approaches and passes the focus, which is sort of the whatever it's rotating around, and slower as it moves away from the focus. Or it goes faster when relatively straight and slower when turning, or vice versa for D, it goes slower when it's relatively straight and faster when it's turning. So again, I know you don't have much context to go off of here, but just take your best guess and we'll review it together. All right. Okay, looks like we're a little bit torn between goes faster as it approaches passes focus, or it goes slower when it's relatively straight and faster when turning. And honestly, you could consider sort of B and D correct, though B is indeed the answer, the most correct description. It's sort of like a slingshot, and that's often the term they use, is the satellite is sort of swinging around the focus because that's where the gravitational force is going to be greatest. And I have a little drawing here to hopefully clarify some of this. But it looks like some of you have a good understanding of this already. So in an elliptical orbit, again, this is assuming that we are 150 kilometers above the Earth. And can anyone remind me why that's important? What is not present when you're 150 kilometers off the surface of our planet?
The atmosphere.
Yes, so there's no air, no drag, right? And so in an elliptical orbit, the satellite moves faster when it's closest to that focus. You can see it right here. So that's sort of the faster motion as it comes around that corner. And then it's sort of shot off at a very fast speed, but then it slows down as it gets further and further away, right? It's sort of like you can imagine the gravity is throwing it out and then slowly dragging it back inwards. And there's a couple little like animations you can find on the internet that display this really well. And I like this diagram here because it kind of shows you how intricate this all is. You can look at how the moon is orbiting our planet, the Earth. It has an elliptical orbit. There's what's called the apogee, which is when the moon is furthest away from Earth, and perigee when it's closest to the Earth. And then the Earth is also has an elliptical orbit around the sun. And so we are what's called perihelion, is when Earth is closest to the sun, and I think it's either aphelion or aphelion is when we're furthest away. And again, I don't know entirely some of the details. I do know that one kind of common misconception is about seasonal stuff. When Earth is closest to the sun, does anyone know what season it tends to be in the northern hemisphere? Do you think it's summer, fall, winter, spring? Want to guess? Did I hear summer? And that was my thinking as well. I used to think, okay, we're closest to the sun, must be like the hotter time period. But actually, as far as I understand, it's actually wintertime tends to fall more here. And summer is more when we're at the furthest point. Though again, I think that's a little more complicated than just having the seasons fall then. But the seasons, fall and winter and summer, are actually due more to Earth's tilt towards the sun rather than the distance between the sun and the Earth, which anyway, it's kind of interesting. Okay, but that's what's going on with elliptical orbits. So again, just think of it as a wider circle. The satellite is moving faster than 8 kilometers per second, so it's not following that perfectly circular orbit. It's got a wider orbit. Think of it as sort of traveling outwards and then coming back, and it slows down as it's furthest away and speeds up as it comes closer together. Okay, last question that I want to ask using Poll Everywhere. This is an open-ended question, so again, I just want to see how this works using Poll Everywhere. Again, not something that I expect you to have any background knowledge of. I just want you to take your best guess. The question is, what is geosynchronous orbit? So I would kind of break down that word. What do you think geo means? What do you think synchronous means? And again, no right or wrong answer here. I just want to see what you think, and then I'll sort of explain what the definition is. It's a little complicated, but take your best guess. All right, let's take a look. Same orbit as Earth, something related to the Earth and time. We think of synchronous as relating to time. Exact same elliptical orbit as another object. All right. Earth materials that are floating around in orbit. Yes, there are definitely satellites that humans have launched that relate to that. Orbit that revolves around the Earth. Has the same period of rotation. Nice, someone definitely knows their definition there. That's a good one. How long the Earth takes to, how much time the Earth takes to move completely, it's going to relate to that. So great. All right, you are all thinking you're on the right track. And I see some people I think have definitely jumped on Google possibly to look this up. Great. Okay, so in the book, to first understand what's going on with this idea of geosynchronous orbit, you've got to understand how satellites can orbit our planet at different distances. So it turns out that some satellites rotate very close to the Earth. You can see here in this diagram here in this polar orbit, here's a satellite that's really, really close to the surface of the Earth. These satellites, the closer you are to Earth's surface, the faster these satellites have to travel. And in fact, since they're traveling really fast, they rotate around our planet pretty quickly, usually about every 90 minutes. So think about that. Every hour and a half, one of these satellites is doing a full circle around the Earth. And that's just to maintain its orbit, because it has to make sure that it doesn't fall down. However, a satellite that's much further away, over here they call it geostationary, but I'll again talk about what geosynchronous means. But if they're further away from the Earth, there is actually slightly less gravity. This is not like saying there's zero gravity, but there's just the gravitational pull is just a little bit smaller. And so they're able to actually stay in orbit while going a little bit slower. So, they rotate around the Earth, say, perhaps every 24 hours. And that's exactly what some of you are getting at in your definitions. So it turns out that at a distance of 5.5 radii, 5.5 Earth radii, I should say, which is the equivalent of 22,000 miles. So if you can get a satellite that's 22,000 miles, imagine that distance right there, that's 22,000 miles away from the surface of the Earth, those satellites are able to stay in orbit and have a rotation period of 24 hours, right? It takes 24 hours to do a full circle around the planet. And I'm hoping you recognize that number. 24 hours is also how long it takes Earth's surface to make a full rotation or full spin on its axis. And so since these match up, these satellites are able to stay over a single point on the surface of the planet at all times. It's almost like they're tethered there. If you can imagine a satellite that's directly above you, except it's 22,000 miles up and it doesn't move, right? Even as you are rotating around on the surface of the Earth. And that's what geosynchronous orbit is describing. And a lot of you had some good definitions there. But to put it simply, it's satellites that can stay above one spot on Earth permanently. Now, I don't know entirely how this works with Earth's wobble, right? Earth does wobble back and forth on its axis, so I don't think that geosynchronous orbit is perfect, or at least there's adjustments that have to be made. But satellite TV, satellites, a lot of cell phone satellites work this way, right? That they sort of cover a certain region on the surface of our planet because that's the region that they are suspended over in a permanent orbit, which is kind of cool. Okay. Last thing to talk about is what the textbook calls escape speed, but I prefer to use the term escape velocity because velocity is taking direction into account, and the direction we're talking about is moving away from our planet. So it's exactly what it sounds like. Escape velocity is the speed and direction needed to escape the gravity of a planet or a star. So this is how we get things off of Earth and out of our solar system. So Earth, it requires 11.2 kilometers per second. If you want to launch something off the surface of the Earth and never have it fall into orbit, never have it come back or circle the planet, it has to be going at a speed of at least 11.2 kilometers per second. And the book goes on to explain the energy stuff around this. Don't worry too much about that. The point is that that's the minimum speed. If you send something off the surface of the planet with that speed, it's not going to fall into orbit. It's not going to have an elliptical orbit. It's just going to continue outwards. But it turns out, and I didn't realize this or think about it, but escaping Earth is not the only thing that matters. If we are able to get a satellite outside of Earth's gravitational influence by achieving the speed, that satellite might still fall into orbit around the sun because the sun has really huge gravitational force influence on everything around it. So the satellite's actually going to have to speed up even more. If we want to send something out of our solar system to get away from the sun itself, it has to accelerate to 42.5 kilometers per second. That is the required speed to get away. And NASA has done this. There is a satellite called the Pioneer 10. That's what's pictured here. It was launched in 1972. I think in 1984, it passed Mars. And then they did a couple of these like slingshot events, sort of like what we were talking about with the elliptical orbits, where they swung the satellite really close to Jupiter in particular, and the gravitational sort of the speed that it gained from briefly rotating around Jupiter sort of shot it out into space. And so now it is it's gone. It's out of our solar system. It is in interstellar space. I don't even know if they're actually in radio contact with it anymore. It's just sort of out there, and so it might crash into something. It might have already been destroyed, or perhaps some other form of life might find it. It's sort of like an ark. They put a whole bunch of information on their human history and biology and all that sort of stuff. It's kind of interesting. So, but those are the escape velocities needed. Your book has an interesting little table that then sort of summarizes the escape velocities needed right here, or escape speeds, to get away from certain astronomical or celestial bodies. And it's not surprising that this sort of relates to the idea of gravity, right? We learned that gravitational force is directly proportional to mass. The more massive something is, the more gravitational force it exerts, and therefore you're going to need a much higher escape speed. So it's not surprising that the sun requires 42.2 kilometers per second. The sun is the most massive thing, but it's also really far away. Whereas then you've got something like Jupiter, which has a lot of mass and is much closer, and so it's got a very high escape speed. If you were on the surface of Jupiter, it'd be very hard to get a satellite away from that. There's Earth as sort of our reference point, and then not surprising, something like the Moon, which is very, very small compared to these other planets, has a very low required escape speed. So if you think about astronauts that landed on the Moon and visited, it took a lot more energy to get those astronauts off Earth and flying towards the Moon than it did for them to then leave the Moon and launch off from the surface of the Moon, because it's a much lower required escape velocity, only 2 kilometers per second. Okay, so I know that I just sort of threw a lot of numbers at you, and so I kind of made this last summary slide. These are the important things I think to take away from this. 8 kilometers per second is the horizontal speed needed to achieve that circular orbit, right? So you can see that right here, the one that perfectly matches the rotation of our planet, that is a circular orbit. If you're a little bit higher than 8 kilometers per second, maybe 10 kilometers per second, something like that, then you're going to have an elliptical orbit, which they don't show here, but an elliptical orbit would look like this, where the satellite swings outward, but then does return. It's just sort of cutting a wider circle around Earth, which would be the focus. To launch something away from the planet, to not have it fall into orbit, you have to have a horizontal speed of at least 11.2 kilometers per second, right? And you can see that here. This is not going to return. That's your escape velocity. However, that satellite could still be picked up by the sun and rotate around the sun, just like our planet Earth is rotating around the sun. So to escape the solar system, to get away from the influence, that's the highest speed, 42.5 kilometers per second at least. And again, your textbook has a long explanation of the energy requirements and stuff and how all that works, but that is the gist of chapter 5. Okay. Any questions on that or comments? Okay, you'll do a little reading and we'll have a little reading quiz on that as part of your homework as well. Okay. The remainder of class I wanted to dedicate to just get going on the Rube Goldberg project stuff. Your goal as part of your homework for Monday will be to put together and film your simple machine. It is a Flipgrid assignment. So here we're looking at task number 4. The first link right there is just a link to the project description again. So if you're forgetting what it is we're trying to do here, this is the same project description I shared with you earlier. Good thing to reference as you start to work on the project. But then I summarize down here what it is I would like you to do. So there's a Flipgrid assignment. Here's what it looks like. I posted my example video. It's the same one I made last week. And I want you to do pretty much exactly what I did. Put together a simple temporary Rube Goldberg machine at home. You should use at least 4 or 5 different items that interact in at least 3 different, unique ways. Your video should start off with you explaining the different components, right? Walk us through the machine. Like, here's the start, and tell us what should happen, right? Then activate it and see if the machine works. It's okay if you need to help it along a little bit. You might need to push something, but you should have a video of your machine going to completion, right? All parts of it should be activated either on their own or with you helping them out. So again, this is just meant to be fun and to help you through it. Again, I've got the description here, so you can look here for details or materials if you're looking for that, and I've got my video posted there as well. So I'll give you the remainder of class to work on this, or at least get started on it. You don't have to have your Flipgrid post made by that time, but I want to give us until 2:55. So that's going to give us just about 20 minutes from now to work on it. So we'll come back together at 2:55. Just touch base on what you did, and you can ask me questions. I'll be here listening the whole time. So if you've got questions, or if you want ideas, or if you've got some weird situation you can't find any materials, I can try to help you with that. But for the next 20 minutes, just try to put together a simple machine, test fire a couple weird materials, see if you can find a location to set up your temporary machine, and then we'll check back in. So again, come back here to the Zoom room at 2:55. We'll check in then. Go for it. I was just checking out a few videos posted by some kids. If anyone knows Cesar, he posted an awesome one in my 8th period, and Zach, yours looked really good. I was just about halfway through it, but had some cool stuff set up. So anyone able to try at least a few things or make a plan? Again, if you're looking for inspiration, those videos that were posted in the earlier post are, I think, really good ones. But again, don't worry about it if you weren't able to get it done now. It will just roll over into homework. And so just to show you homework for Monday over the weekend is to post to that Flipgrid of your simple Rube Goldberg machine, meeting those basic requirements. Read Hewitt chapter 5.12 and just take some notes for a do now reading quiz that we'll have when we start the next class. There's no reading check questions or anything you need to do. As you start to put together your machine, what I want to emphasize is the word simple, right? This is just something temporary. Please keep it simple. You don't have to go totally crazy. Don't try to fire a projectile from across the room or whatever. Don't drive yourself too crazy doing that. The other thing that I've learned when putting it together, and I think some of you are realizing, is that everything's got to be pretty much on a hairpin trigger, right? Like it shouldn't have to work too hard to make something happen. Like if you're going to have things knock each other over, then they've got to be pretty wobbly to start with, right? That is the best way to go about it. And I recommend too, the way I did it with my daughter's toys was, I had all these things and I was like, okay, well, this could knock over that. This could be fun to do, and add all these components. And then the trick then was just how to sew those together. How do you get one to activate the other? But it could be fun. So another part of that is to come back and check out other people's videos, because it might inspire you if you're not sure what to do just yet. And also leave each other some positive feedback. I think it's just always a good thing to do. Okay, that is all I have for you. So I'll hang around here if you have any questions or if you want any advice or anything else. But otherwise, thank you very much. Have a good day. You're all set.
Thank you.
Thank you.